So thanks for coming. So today we have the Seokbeom who will give his first talk at this Discrete seminar. And we'll talk about tournaments, right?
Right.
Some free tournament. Okay,
Thank you.
We will see.
Okay. Okay, thank you for the introduction and thank you for coming. Today I'm going to talk about some structures of tournaments. And also I have to say that this is joint work with Taite LaGrange, Mathieu Rundström, who are both PhD student at the University of Waterloo, and Arpan Sadhukhan, who is now a postdoc at the Indian Institute of Technology, and also Sophie Spirkl, who is a professor at the University of Waterloo. And also this project was mainly in progress during my visit at University of Waterloo last year. And I have to thank Sang-il and Sophie for supporting this visit. Okay. And if you're not familiar with tournaments, and even if you do not know what tournaments are, don't worry, because I'll start with really basic definitions. So let's look at what tournaments are. So a tournament is just an orientation of the complete graph, which means that for any two distinct vertices, there is exactly one edge between them. And in this talk, I'll call directed edges as edges because most of the edges will be directed. And as you might guess from the title, there will be lots of tournaments in this talk. And I do not want to explain them by explaining what those edges are directed in either way. So I'll just introduce a nice way to describe those tournaments in terms of graphs, which is called a baggage graph. So the idea is as follows. So if you just fix a vertex ordering of the tournament, then each edge will go either forward or backward under that ordering, right? So instead of listing all of their directed edges, I'll just give an ordering and give a list of edges going backward. Then from those informations, you can reconstruct what the original tournament was. And formally, given a tournament and its vertex ordering, the baggage graph with respect to that ordering is just an order graph whose vertex set is same as the tournament, and two distinct vertices are adjacent in this baggage graph if and only if the direction edge between them goes backward, and the ordering is what we fixed at the beginning. So for example, here is a 5-vertex tournament, and if you consider the cyclic ordering V1 to V5 in this illustration, then among all edges that is incident with V1, there is exactly one edge that goes backward under this ordering, which is V4, V1. So in the baggage graph, V1 and V4 are adjacent. And this is spoiler, but there are two more edges going backward, which are V2, V4, V4, V2, and V5, V3. So in the baggage graph, there are two more edges. And I'm going to talk about some structure of tournaments, and it is not interesting to describe the structure of all tournaments, so we have to give some restriction on this structure. And in this talk, I'm going to deal with some condition about subtournament. And here, a subtournament S is a subtournament of T if it is just obtained from T by deleting vertices. And we always think about something up to isomorphism. So we say T contains S if T has subtournament isomorphic to S, and otherwise T is just S free. So, and my question is about the structure of S free tournaments for fixed tournament S. But the question is, what's the structure? I think this is related to a more general question. So like something like this. So if someone wants you to explain the structure of some graphs or tournaments in the class that is class undertaking induced subgraphs, then how can you describe them? I think there are several ways to do this, but I think there are three basic and fundamental ways to do. And the first one is giving a list of forbidden induced subgraphs. So because these classes are just downward closed, so there might be some minimal non-elements. So giving the complete list of them, you can just describe the class. And the second one is about the property. And here I do not know the exact definition of property, so please do not ask me, but I want to just say that there are some classes that have a list of forbidden induced subgraphs, but it has a better way to describe them. For example, if you have bipartite graphs, then you can just describe them by saying some cycle thing, but you can just say they are just two colors. And the third way is giving a construction. Again, I do not know the exact definition of construction, but the general scheme is like there are some basic graph classes and there are some operations so that you can build any graph or tournament in that class starting from those basic graphs by applying iterative those operations. So for a toy example, if you want to explain what edgeless graphs are, then you can just say that there are graphs without the complete graph and two vertices and inducer graph. If you want to describe as a property, then you can just say any two distinct vertices are adjacent, right? I think they're equivalent. They're all equivalent, right? And if you want to construction, then you can just say you start from one vertex graph and take several disjoint unions. Okay, under this scheme, let's come back to our original question. So the first item has a trivial answer, right? The property being S3 always explains what you're excluding. And for properties, I'm not sure. Someone might tell me that being S3 is a property by itself. And I do not want to make any conflict with them, so I'll just delete the second item. So there's exactly one unsolved question here. So our main interest is about the construction of S3 tournaments. Okay, and this is a really interesting and important question, but it is really hard because if you look at the graph case first, there is a really small number of graphs that gives a positive answer for the previous question. So for graph H, we say a graph is H-free if it has no induced subgraph isomorphic to H. And even for the construction of H-free graphs, this is a complete list of H that has a positive answer. The first two items is easy, right? For a excluding a path with most four vertices, it is kind of basic classes, which is called cographs if it has exactly four vertices. And also, if you know the structure about graphs without the complement of H, you also know the H-free graphs, right? You can just take the complement. And except for them, there are only 4 results about in this way. And for Paul-free graphs and diamond-free graphs, they have a kind of easier answer because it is known that every connected Paul-free graph is either triangle-free or a complete multipartite graph. And for diamond-free graph, there is a nice construction by using bipartite graph. And I do not want to be in detail. And for cloud-free graphs and bool-free graphs, there are also construction for them, but they're really involved. So I do not want to get in detail either. And this is what we know for graphs. And let us again come back to the tournament. And as this problem is really hard, let us look at the case when S has small number of vertices. But if S has at most 2 vertices, we do not need to answer the question because it's really easy. So let us start with the case when S has 3 vertices. And if you exclude the cyclic triangle, so it is an orientation of the triangle such that each vertex has algebraic 1, then this is one of the basic classes of tournaments which are called transitive tournaments. So it is known that a tournament does not contain a directed triangle if and only if it is acyclic. That means it does not contain a directed cycle as a subgraph. And also, it admits an edgeless baggage graph, which means that there is some order on the vertices so that every edge goes forward. And in particular, the last item gives a construction. Because you just start with 1 vertex graph, and if you have 2 transitive tournaments, you just take a disjoint union of them and put all edges in the same direction. Then this always gives a transitive tournament, so this is a construction. Right. So for 3 vertex tournament, the remaining case is for the transitive triangle. And for this, we will look at the Stern's theorem, which is a Ramsey type theorem for tournaments. And which means that if your tournament does not contain a k-vertex transitive tournament, then the tournament must have less than 2 to the k minus 1 vertices. So this means that if you exclude a 3-vertex one, then your tournament can have at most 3 vertices, and among them, TT3 is the only one that contains TT3, right? So you even do not need a structure theorem because there's a finite list of them. And this is all about 3-vertex tournaments. But from the 4-vertex tournaments, it becomes a bit harder. And I think the easiest one is the strongly connected one. So I'll just call S4 for the strongly connected tournament on 4 vertices. And I want to say this is unique up to isomorphism. And the structure theorem for S4-3 tournaments is known by Moore's theorem. And here, Moore's theorem states that every strongly connected tournament is vertex pancyclic, which means that if you take your favorite vertex, you can always find a directed cycle of any possible length that contains your vertex. So this means that if you look at, I'll just use the board. So if you look at your tournament, and if you look at one of its strongly connected components, and suppose that it has at least 4 vertices, then by Moore's theorem, it will always contain a 4-vertex directed cycle. And these 4 vertices will induce S4, right? This means that if you have S4 free tournament, each connected component, strongly connected component, will either be a 1-vertex or isomorphic to a cyclic triangle. And also this gives kind of construction.
What was S4 by the way?
S4 is just the thing here, the strongly connected tournament on 4 vertices.
Oh, is it unique?
Yes, it's unique up to isomorphism. So by Moore's theorem, this gives a construction. But other than these results coming from some classical theorems, there are only 3 tournaments up to reversing all the edges, such that the construction for S3 tournaments is known. In the first item, the bar S means just a reverse. So which means that you reverse all the directions of the edges in S. And other than, yes, there are only 3 tournaments, which are called D4, W5, U5. And you do not need to remember these things because I will not deal with them maybe only once. And at that time, I'm going to just recall it. Any questions so far? Great. So from now, I'm going to introduce my main result. So in our main result, we're again excluding a new 5-vertex tournament, which is called the delta 122. And this name is a bit weird at first glance, but it has some natural meaning because if you partition those 5 vertices into V1, V2, V3, and V4, V5, then if you look at the edges between these partitions, they all go like this way. So they really act like a cyclic triangle. So this is why you use delta in the notation. Okay, so this is the tournament what we're going to exclude. And if you look at the cyclic ordering under this figure, you can have this baggage graph. So in fact, this is obtained from a transitive tournament by reversing 2 edges. Okay, and our main result is the structure of tournament excluding this one. And to prepare the statement, we have to need some definition. The first one is the monotone path. So what is a monotone path? Is just an induced path in the order graph, such that if you look at the sequence of indices, then they're monotone. Okay. So if you look at this figure and look at the path with olive-colored edges, then this will be a monotone path, right?
So monotone, you don't care about the tournament that you're working with. It's just a sequence of vertices.
Yes, right. Oh, pardon? Could you see?
There's some tournament that you're thinking about, and you
Uh-huh.
don't care whether the monotone path is a path in the tournament or not.
We are going to. So I'm going to say something about the monotone path in the baggage graph. So
Oh,
in
okay.
here we're going to
I
think
see.
about in the order graph sense.
Oh, in the so it's a pass in the baggage graph.
Yeah, right.
So it's going to always go backwards.
Yeah, that's right.
Yeah.
Under the ordering. Any questions? Okay. But if you look at this red colored path, this is not on a monotone path, right? Because I'm not sure which ordering is correct, but it goes forward twice and backward once and again forward once. So this is not a monotone path. And also, I'm going to define 3 more order graphs, which are called H5, H6, and 7. And again, you do not need to remember what these are, because I will always give you some illustrations and figures. And there are just 2 things that you have to remember. The first one is that all H5, H6, H7 are connected. And for H6, we call these the first 3 vertices and the last 3 vertices form blocks of H6. So, any questions about the definition?
In what sense they form a block?
Pardon?
In what sense do they form a block? There's edges, like several edges between these two, right?
But we're just saying the set of vertices. So in
Nothing to
H6
do with the block of the.
Yeah,
so
block
what's
of
the
H6.
definition of a block?
Both color classes are called a block.
Yes, they're
Yeah,
just
so-
called
Ah,
a
so
Yeah,
is it?
nothing to do
Yeah.
with the.
nothing
Okay.
without some block of
Nothing to do with the two connected graph.
Yeah.
Hmm.
Other questions? Okay, now let's look at the structure theorem. So it's a bit long, right?
Okay.
But I'll just say, so if you have a delta 1, 2, 3 tournament, then you can always, it always has an ordering, such that if you look at the baggage graph with respect to ordering, then each component is either a monotone path or one of HIs. And in particular, if its component is isomorphic to one of HI, it has more property. So if it was isomorphic to one of H5 or H7, then the vertices of the component must be consecutive along the same order with the one I described in this slide. So for example, if you look at this figure and look at the component with yellow edges, this induces H5, and those 5 vertices are consecutive in the same order. And for H6, it is a bit different, but have a similar property. So all the 6 vertices need not be adjacent, but if you look at each block of H6, then they must be consecutive along the same order. So if you look at this red colored component, those 6 vertices are not adjacent, but if you look at each block, they're adjacent. They're consecutive with the same order.
Sorry, so this delta 1 to 2 free tournament, is it always a tournament on 5 vertices, or can you also define this for larger tournaments?
Could you say one more time?
So delta 1 to 2 freeness,
Uh-huh.
so this delta 1 to 2, is it always a tournament on 5 vertices?
Yeah, this is why I did
For the concrete values, but you could
this one.
put in like K, L, and T, and
Yeah, that's right.
But this special theorem is only for 1, 2.
yeah, that's only for
Only
the
for
for
this
one.
one, yes.
Only
Right.
For one tournament. You cannot change the values, right?
Yes, right.
At this moment.
Yes.
Can you reverse the 2 blocks, or did the 2 blocks like themselves come in the same order?
That's a good question, and they cannot be reversed. So the first block must be precede the second one. Any other questions? questions?
And this is if and only if.
Yes. I think not, because there are okay. I have to say that because even for delta 1 to 2, there's a baggage graph looking like even for delta 1 to 2, there is a baggage graph looking like this one. So if you so this is not, each component has a momentum path, but this is not delta 1 to 2 free, right? But I think this is the only baggage graph that they kind of conflicts the result.
Oh.
So we was able to add this in the conclusion, but it was already contained in the assumption. Any other questions?
And
Mm-hmm.
is maybe part of this, but you found large tournaments that can not have this structure, right? If delta 1 to 2 can have a ordering that have this structure, and if any graph can have this kind of structure, then it is meaningless, maybe. So there is a large tournament.
So you mean
cannot
that there is some?
any-
Uh-huh.
yeah.
So you mean are there some tournament that satisfies the conclusion with large number of vertices, but it is not delta 1 to 2 free?
Yeah, it's not delta 1 to 2 free, and for any vertex ordering, it does not have this structure.
Are there some tournaments that don't admit such an ordering?
That's a nice
I
question,
see,
and
so
I
if-
think, if you just take a regular tournament with large number of vertices, then if you look at the first vertex of any ordering, all of this neighbor becomes
Oh yeah.
adjacent to this vertex, right?
Mm.
So it always does not satisfy this one.
All of you neighbors
So it has a large number of in neighbors and out neighbors. All the in neighbors are back in the backhash graph. So this can't be a monotone component. And it can't be one of the 3 examples because they all have bounded degree.
Oh, I see.
Any other questions? Great. And there will be lots of questions because the backhash graph is kind of not very kind thing to describe the properties tournaments, and I agree with it. So from now, I want to translate this theorem into the word of tournaments. Okay. The first thing is to reveal what H5 up to H7 are. And indeed, they are just baggage graphs of some specific tournaments, which we call a T5, P7 minus, and P7. And for P5, this is a vertex transitive tournament on 5 vertices, and this is again unique up to isomorphism. And for P7, this is the Paley tournament on 7 vertices, and for P7 minus, this is something obtained from P7 by deleting a vertex. And again, you do not have to remember a lot of things, but just I want to emphasize one thing, that in P7, if you look at the block, 3 vertices in each block, they induce a cyclic triangle. And between those 2 blocks, there's kind of directed matching going backward. This is the only thing that you need to remember. For other things, forgot everything, okay?
So T5 is a graph tournament for H5, etc.
Yeah, that's right. So each graph, order graph is a baggage graph of the tournament with the same number of vertices. And from now, let's reveal some properties. So remember that for components isomorphic to H5 or H7, the vertices must be consecutive in the same ordering. Right? Then, if you look at this set of vertices in the complement, and if you look at vertex before that, it will only contain, it will only have out neighbors in this, right? Because there are no edges. And if you look at the vertex after that, it will only have in neighbors, right? So this is something what we call a homogeneous set in tournaments, which are also called modules. So formally, set of non-empty set of vertices is called a homogeneous set if every vertex outside that set has only in neighbors or only out neighbors in that. And if you have a homogeneous set, which is not on one vertex set or the whole vertex set, you can always decompose the tournament into two subtournaments under the operation called substitution, what I'm going to explain now. So what is the substitution? So you start with two tournaments, S1 and S2, and fix a vertex V in S1. Now, substituting S2 for V means you delete V from S1 and add a disjoint copy of S2 in here, and add all edges between them according to the neighbors of V. So as you might see, if you apply a substitution, then this created tournament, the vertex of this one will be a homogeneous set. And also, conversely, if you have a homogeneous set, then you can always decompose it under this substitution operation. So our structure theorem means that in terms of tournaments, if a delta 1, 2, 2, 3 tournament contains T5 or P7, then the set of vertices in them will be a homogeneous set. So you can just decompose along this according to this substitution operation. Okay. So substitution is the thing we need to generate all delta 1, 2, 2, 3 tournaments. But we're still missing H6, right? So let's look at the properties of H6. So if you look at H6, you cannot say that each block is a homogeneous set in the tournament, because if you look at this set, the first block, and if you look at a vertex in the other block, then it has both an in neighbor and out neighbor, right? But this bad thing happens only when we pick a vertex in the other block, right? So if we delete this not the other block from the tournament, then the remaining block will be a homogeneous set. So, and this is what we call a homogeneous pair in the theorem tournament. And formally, a pair AB of disjoint sets of vertices is a homogeneous pair if when you delete A from the tournament, then B becomes a homogeneous set, and also vice versa. And similar to the relation between homogeneous sets and substitution, there is an operation called join, which creates a homogeneous pair. But as you might guess, we only deal with homogeneous pairs that induces P7 minus the tournament by our structure theorem. So let's just focus on about creating this one. So you pick an edge, say it is VU, and the rest of the vertices will be partitioned according to its in neighbors and out neighbors. And instead of U and V, if you apply P7 join to this edge, then you put each block to the ends of the vertex, and between them you add a suitable edge so that these 6 vertices induce P7 minus in the tournament. And between these 6 vertices and the rest of them, you add edges according to the adjacency between UV and the rest of the thing.
So the resulting thing may not be a tournament now?
Oh, so I omit all the edges going this way.
Okay.
So these yellow things are just what I said in here. So again, similar to the relation between homogeneous sets and substitution, if you have a homogeneous pair, you can decompose it along this join operation, and conversely, applying this join operation results in a tournament having a homogeneous pair.
So you pick like matching or in general?
Yeah, there's needs some restrictions, right?
Huh?
So what?
Maybe
So
one of the four areas is empty, or it has to be empty on your, when you choose, you can't choose, like in the previous operation, you could just choose any vertex. And it'll be, some will be to the left and some will be to the right. Here you choose an edge, but you can't choose an arbitrary edge necessarily, because you may have, after the join, it looks like you'll not have, like the two parts of the join split the remaining vertices up into three parts.
Yes,
So,
right.
Yeah.
And yeah, that's right. So we cannot apply a join operation to any edges in this more conditions.
Okay.
Ah, I see.
And that was exactly what I was going to tell next
Sorry.
slide. No problem. Any questions about this joint operation? Okay. So, in summary, if you have H5 or H7, then it is related to a substitution. And if you have H6, it is related to a P7 minus join. Right. So our theorem can be described in terms of construction. But before that, I'll just say a tournament is a paving tournament if it has a baggage graph such that every component is a motion path. And I'm not sure why we call this a paving tournament, but at some point we decided to call it. And in terms of construction, we say the following. So if you have a delta 1, 2, 2, 3 tournament, then it must satisfy one of these four options. The first one is it is isomorphic one of these T5, P7 minus P7, or it can be obtained from smaller one by substituting T5 for P7 minus or P7 for a special vertex, or applying P7 join for some special edge. And one might wonder why this is here, and I think
Oh, they could be right next to each other.
Yeah,
Close.
that's right.
Yeah, okay.
right
Yeah, fair.
exactly.
So I didn't get this.
Oh, so the issue is that if
There was an issue previously because there could be something between the blocks in the
Yes.
ordering, but they could also just be next to each other.
right,
And
if
then
there
it
are
is
no vertices like this,
homogeneous again.
then these becomes a homogeneous set. And the last item is it is a paving tournament. So for example, let's look at this example. Then if you want to construct this, you start with this paving tournament, and you pick this vertex, and just apply a substitution. And again, you pick this edge, and you apply a P7 minus join. So this is a sequence of operations that creates our example. Any questions?
So when you apply this join, why are the right and the left parts not symmetric in terms of the back edges?
Yes. So indeed, you do not necessarily always need to pick kind of baggage to apply P7 join, because we are applying P7 to edges in tournaments.
No, sure, but after you made this join, you would have added two triangles and then this back matching, right?
Yes, right.
And with respect to these two triangles, if I look at the back edge graph of these two extra triangles, the back edge graph of both the triangles should look the same. I mean, modulo how you arrange the vertices of these triangles in this order. I mean, I'm just wondering why the left-hand side red graph has two edges between them, but the right-hand side only has one in the back edge graph.
So you mean there's some asymmetry between them?
Yeah.
Because I used some different order to ensure that they are connected. So if you change the ordering between these two, then you can obtain something like this.
Which is disconnected.
Yeah,
that's what you are worried about.
Yeah, that's right.
Wait.
The
The
middle
back
vertex.
edge graph?
Back edge graph is.
Okay.
This is pretty good.
Yeah, it is pretty bad. It is not a component anymore, right? Okay. Any other questions? Okay.
Yeah, I mean, I assume you're gonna tell us what like a special vertex and a special edge mean, or are you not going to?
I can tell you what special vertex is. Special edges, it is a bit technical. So for special vertex, it's really easy. So towards the ease. So we say a vertex.
I mean, it needs to be an ordering where it's isolated, right?
It's
that what you need?
not necessarily,
Okay.
because we say a vertex. We want vertex special. When x, we say x is a special vertex. When there's no, say y, z, z prime, such that if you look at x, y, z, they form a cyclic triangle. And also if you look at z prime, they form a cyclic triangle. Like this thing. So it is easy because if you just substitute a two-verse tournament in here, you create tilde 1 to 2. Right? But also, if it doesn't have this property, substituting does not matter. And for edges, it is a bit technical. So I must say, just in some sense, it is an isolated edge in the back edge graph. In some sense. So this is why I give an illustration such in this way.
Yeah, so special is like supposed to mean that when you substitute it in, you don't create
Create
one of these.
another copy of it.
Yeah.
Any other questions? Great. Okay, so this is a really strong theorem because it completely dissolves the structure. So I'll just explain some applications of our result, which is my favorite. I'm going to talk about some coloring of tournaments, which is indeed a die coloring. So a die coloring means just a partition of the vertex set such that each part induces a transitive subtournament. And also the dichromatic number is just the smallest number of colors needed to do a die coloring. So by using our structure theorem, we was able to find a tight upper bound for the dichromatic number of delta 1 to 2 free tournaments. And we proved that there are always 3 die colorable, and they have dichromatic number and exactly 3 when it contains P7. And this proof was not that hard because there is a nice connection between the die coloring of tournaments and a proper coloring of its baggage graph. Just because, as this lemma says. So this lemma says that if you have a proper coloring of the baggage graph, then it always gives a die coloring of a tournament. And this is because if you look at each color class in the baggage graph, they are stable sets, so they will induce a transitive tournament in the original tournament, right? And in particular, if you remember what H5 and H6 were, you can check that they have proper two colorings in terms of just graphs. And also monotone paths are properly two colorable. But for P7, you can check that it is not 2-die colorable, but indeed it is 3-die colorable. So because of these observations, we was able to figure out the dichromatic number of such tournaments. And the another application is related to the ergotino type thing. So let alpha of t be the order of largest transit subtournament of t. And in fact, those, if we deal with delta 1, 2, 3, 3 tournaments, then we have a trivial lower bound n over 3 because they are always 3-die colorable, right? But we somehow proved a stronger thing, right? We exactly figure out when they are 3-die color, when the chromatic number is exactly 3 or not. So by using that property, was able to find the type bound. So we proved that they always contain a transitive subtournament of size 3n over 7, and this is the best possible. And again, the proof is not very hard. I'm just going to do this. So we know that such tournaments are 2-die colorable when it doesn't contain P7. So in that case, it has such subtournament of size at least n over 2. And if it contains P7, if you use around 30 seconds or 1 minute, you can check that P7 contains a transitive set of size 3, but not 4. So because of this observation, we obtained this bound. And indeed, this is best possible because if you consider a tournament obtained from transitive 1 by substituting P7 for each vertex, then you can easily check that the lower bound holds. Any questions?
What is the value for alpha bar when t is delta 1 to 2? Is it?
It is 3, right?
So that is.
Then we have an independent size of strictly larger than n over 3 in general case. So then can we also consider, if you consider kind of fractional chromatic number of this delta 1 to 3 tournament, then can we improve the bound of 3?
For fractional version.
Yes.
That's a good question, and I'm not sure. I have not thought about the question. I'm not sure about that part. We can just discuss it after that.
A very dumb question. For delta 1 to 2, the size of the largest subtournament should be, transitive subtournament should be 4, right? Well,
oh yes, right, sorry.
Okay, alright.
Yeah.
Right.
Yes, very quick.
Yes. Any other questions?
Is there any chance that this might have a very easy proof without using structure theorem?
I'm not sure.
What is bound?
Like some induction, I don't know.
I'm not sure. Mostly. Well, I have not thought about that one. So. Any other questions? Great. So I have around 15 minutes or 5 minutes. So I'll just go into quick about some proof strategies. So it is not, the overall proof is really simple, but in saying this way, one might say that the proof of strong perfect graph theorem is so simple.
Yes.
But just I want to say that the hardest part in this proof was the showing that if we exclude delta 1 to 2 together with T5 and P7 minus, then they are paving tournaments. And this indeed contains a lot of case analysis. And fortunately, due to some lemma, we was able to reduce the number of cases to less than 10, and which is affordable for structural graph theorists. So this is what we call the fuzzy lemma. So this is called as follows. So the proof is, if we base on induction, and suppose that you have a delta 1 to 2 free tournament, and there's some vertex, say x, such that if you delete that, you obtain a paving tournament. And let's just sigma be ordering on t minus x, with missing this. Then there is some kind of window here of size n-4, such that if you look at the vertices before this window, this x will have at most one out neighbor. And if you look at the vertices after this window, then this x will have at most one in neighbor in this. So almost all neighbors of x is determined by this fuzzy lemma. So we was able to just guess the correct position of x in sigma and kind of try to reorder some small number of vertices to obtain some nice ordering of the whole tournament. Yes, I think this is a nice lemma. And from now, I'm going to talk about some open problems before I end this talk. I think I like this topic a lot, and I have lots of questions, but in this talk, I'm going to explain some question related to the construction. So still we're interested in excluding a tournament with 5 vertices, and there are lots of lists, and among them I'll introduce 2. The first question is related to prime tournaments. Here a tournament is called prime if all of its homogeneous set is either a singleton set or the whole vertex set. So it does not admit a decomposition along the substitution. And one of the classic results by Erfeld and Rosenberg showed that if you have a prime tournament with at least 5 vertices, that it will always contain a prime tournament with exactly 5 vertices. So we want to exclude one of the 5 vertex prime tournaments, and surprisingly, there are only 3 of isomorphism. And here, if you remember the introduction, you already saw W5 and U5, and which says that there's a structure theorem for U5 free tournaments and W5 free tournaments. So there's exactly one unsolved question. So what is the structure? Because construction for T5 free tournaments. And the second one is not related to a prime tournament, but I'll just introduce another tournament called Delta 11C3. So it is again a 5 vertex tournament obtained from the cyclic triangle by substituting another cyclic triangle around one of its vertices. So which means that you have a cyclic triangle here, and you have an edge, and it looks like this. And I want to say we say a tournament is liked if it is delta 11C3 free. And the second question is about the construction for like tournaments. And for this question has an important connection with some algorithmic problems about the dichromatic number of tournaments. So in particular, if you are interested in the algorithmic questions about determining if a tournament is 2 dicolorable, there is one of interesting lemma that says that if you have a 2 dicolorable tournament, then it can always be partitioned into 2 subtournaments such that each subtournament is light. And you can even find such a partition in polynomial time. And also recently, Klinghoffer and Newman proved that there is an approximation algorithm for coloring light tournaments. So formally, there is a polynomial time algorithm that colors 2 dicolorable tournaments with 5 colors. So by combining these results, we can obtain a polynomial time approximation algorithm that colors 2 dicolorable tournaments with 10 colors. Right? So another question about improving this second theorem. So because if we can improve the number of colors in this theorem, we can improve the approximation algorithm for general 2 coloring tournaments. Yes?
Is it known that 2 coloring,
It's dicolor. Or it's can be so nobody knows maybe?
Is it? Do you know that? I'm confused by the NP hard, I guess, because it's not a distinction.
Well, is it NP hard to improve the number? So
So
I mean that it is NP. For example, is it NP hard to color two dicolorable light tournaments with four colors?
4 colors so that each color class is light.
It's just a dye coloring. Also, this is just the dye colors.
Each color class would be
Acyclic, right?
I see. So approximation. I guess.
Yes, approximation, right?
And
I mean, the question is like, when you say NPR, is
Yeah, this is
so, or you confirm that graph.
Yeah, yeah, that's
tournament is not too colorful. Or
Yeah, that's
something
right.
like that. Yes or no?
Yeah, right. That's the.
But are we saying that we do not know how to find a two dye coloring of a light tournament in polynomial time, like it's
So exact algorithm.
Yeah.
It is still an open question.
It's deciding whether a tournament 2 dicolorable known to be NPR.
Yes, right.
It is no.
It is no.
Okay.
but in the special case of light tournaments, it's
But if you restrict the input to light tournaments, it is not known if it is hard or not.
Okay.
Any other questions? Maybe you can ask this is the end of my talk. Thank you so much.
Thank you. Right. Any questions? If you remove this condition, then you might have a different class of tournaments, right?
Yes.
Like
right.
starting from this
Yeah.
structure construction, can you think of the forbidden tournaments?
Oh, I see. So you, in our construction theorem, you remove all the special conditions
Yeah.
and look
something
at
look at the forbidden.
the form. So you look at the resulting class,
Yeah.
and if it does not contain something, right?
Mhm.
I think it still does not contain regular tournaments of large size.
Doesn't that give you the still coloring region, the applications? Like, if you have a class of tournaments which has some kind of structure like
Uh-huh.
that, then you can use that to color the resulting tournaments, right?
So, first I'll say that if you remove the special condition, then the resulting tournament, the class of tournaments, has unbounded dichromatic number,
Oh, is it?
because this is simple. So it is to see that it contains the triangle. And I think this is one of the classical example for calling tournaments. You fix one vertex, and you substitute same tournaments for two of its vertices. Then this, if this was, this tournament has dichromatic k, then the obtained one has k plus 1.
So you have to block something.
Yeah, that's right.
Any other questions? Right, if not, let's thank the speaker.